Hello friends, MoNaCo here. Just getting ready for our 5th video note, States of Matter. Wanted to offer your Easter egg up ahead of time for this video. For this video we're going to be covering the states of matter, allotropes, and the diatomic elements. But I wanted to point out something to you. On my home page, I have a link to vocabulary. It's vocabulary links and practice quizzes, okay? For Unit 3 on the periodic table, there is this great website to use. Okay, so I want you to tell me the name of the website that you have to use in order to practice your vocabulary. That's your Easter egg for video number 5, okay? So this video number 5, we're going to focus on the states of matter. Understand that whenever you see a word that you don't necessarily understand, you can go to my quiz off my teacher's webpage, or you can go ahead and do your Google image searches or your Google keyword searches, okay? These types of things are going to make you a more effective student in the long run. So remember, my Easter egg is tell me the name of the website that I use for my online quizzes, and you can get yourself a little bonus. Today we're going to focus on states of matter, which is actually a 7th grade physical science topic, but we twist it a little bit in chemistry. You need to understand the 3 phases of matter, how to represent them with particle diagrams. Pretty simple stuff. There's 2 other things we're going to talk about: allotropes and the diatomic 7. There's 7 elements out there that are special that come in packages of 2. We're going to focus on those. As always, sign up for my text alerts so you can get extra bonus. Read in. What are the states of matter? There's 3: solid, liquid, gas. There is in fact a 4th. It's called a plasma. We don't study that in Regents chemistry really. That's the type of phase of matter that's on the sun or in any glowing tube light. Interactions between the atoms or molecules of matter will change if the state changes. So there's chemistry, it's the study of matter and energy. So matter is solid, liquid, or gas, and all the elements. Energy is how it affects those things. So you put energy into a solid, it turns to a liquid, put energy in a liquid, turns to a gas. That's a later unit. We're just going to focus on some of the particle diagrams today and some of the definitions that we use in chemistry for solids, liquids, and gases. So these are a little bit different than what you know about in 7th grade. First of all, we always refer to them at STP, standard temperature and pressure. In your reference tables, it's the first one that there is. We're talking about 1 atmosphere of pressure, 0 degrees Celsius. Okay? 101.3 kPa is the same as 1 atmosphere, and 270 Kelvin is the same as 0 degrees. So when we're talking about STP, we're talking about that. 1 atmosphere of pressure and 0 degrees Celsius. Now, most elements are solids at STP. Example, carbon, coal, okay? It has a definite volume and a definite shape. You could find that volume by the displacement method or by length times width times height if it was a regular size. Liquids, there are only 2 elements at STP, bromine and mercury, okay? Br2 is a liquid and Hg is a liquid. They have a different volume, definite volume, meaning you could pour them into a graduated cylinder and measure how much you've got, but they automatically take the shape of the container. Think about it. You pour water or any other liquid into a container, it takes the shape of the container. If it's the shape of a flower vase, the shape of a Gatorade bottle, whatever it is, it takes that shape. Now gases, example, like neon gas in the neon discharge tubes with neon signs all around them, they have no definite volume. That is unless they're trapped in the container, right? So unless the container is exactly 2 liters and it's full of exactly that type of gas, that is definitely a volume. But they will always fill the shape of their container. So a gas will always fill the entire container. Even if you add a little bit, it's going to spread out and fill the entire container. So I would say they have no shape or volume. There's your particle models. Solid. Regular patterns. These are all great particle models because they have regular numbers of them. They've got 2, 4, 8, 12 particles in each. You always want to have 4 to 6 particles when you're doing a particle diagram. You guys did a good job on that on our first lab, so I'm not going to spend much time there. Now there's 7 elements that are Siamese twins, which means that when you find them in nature, they're packaged with a buddy. They're unstable alone, so they team up. Okay? They pair up in order to fill their valence shells. So in order to have a happy number of 8 electrons in the outside shell, or 2 in the case of hydrogen, they share with a buddy. Okay? 2 oxygen atoms would have this following structure. Oxygen normally has 2, 4, 6 valence electrons, and another oxygen has 2, 4, 6 electrons. Now, they want to have 8, so they have to share. They'll share 2 pairs. And as a result, we get ourselves a situation that looks like this. 2 oxygens connected like this, and we'll draw 2, oopsies, I want to do black, 2 solid lines in between to show that they're connected by 2 bonds. There's many ways to draw oxygen molecule. All of them are acceptable. Okay, so that's a diatomic element. There's 2 oxygens that make that element O2. Now, they always contain 2 identical atoms and 7 of them. We must memorize it. So use this 7-up trick. I want to show you here. 7-up trick. Look at. If you trace yourself the number 7 right there on the periodic table, there's 7, 1, 2, 3, 4, 5, 6 elements, and up on top, hydrogen. Okay, so there's a number 7 on the periodic table. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine are it. Let's see here. We got there. Make the shape of a 7 on the periodic table. And the up is the H2. Come on there, computer. Work for me. There we go. The up is the H2. I also like to call them Hofbrinkel. Hofbrinkel, because those are the 7 elements that are diatomic. H, of course, being the first one, is up above the rest of the periodic table. Now, an allotrope is a slight change. It's one of 2 or more different forms of an element that are in the same phase, but with different formulas, okay, and different physical and chemical properties. Examples of allotropes of oxygen are O2, and the stuff everyone's heard of is O3, ozone. Ozone's up in the high level of our atmosphere, protects us from ultraviolet rays. It's O3. O2 is oxygen, O3 is ozone. They are the same element, but they're in different forms. They have a different formula. The most common allotrope that we love to talk about is carbon. We're talking about graphite in pencils versus diamonds, or charcoal, okay? That charcoal that you're using to cook the steak during the barbecue is the same element as that really expensive diamond on your fiance's finger. But they have a different formula and a different chemical properties as a result. Okay. So for practice, you want to take some time and write your short answer responses, okay, for the homework prac. You can also do some practice problems on page 13 and 14 of your homework. And remember, your Easter egg is to tell me what website I use for my online quizzes. Thanks for watching.